Good morning, good afternoon, good evening, or whatever time zone you're in. Welcome to the introduction to software-defined networking and Openflow. My name is Warren Finch. I'm one of the full-time trainers for APNIC. We've got a little bit to cover today. It looks like we've only got a small group, so that's good. Make it a little bit more interactive. Before we start, I just want to go over some housekeeping for what we're going to be covering today. So from a point of view of using a online service, if you're using Hoover, you're probably inside the web browser and you've got the session coming through there. Otherwise, if you're using Zoom, there is a few tools I want to point out for you to use. For example, I want you to have a look at the reactions area. It will make it easier. If you can go to the reactions area, and from time to time, I'm going to ask you to react with a yes. So a green tick will be the yes, a red X will be no, or even a thumbs up for agreeing or ready to go ahead. If you have any questions throughout the day, raise your hand and you can unmute yourself and ask the questions, or you're welcome to type those into the Zoom chat area. From time to time, I'll be drawing on the whiteboard. If for whatever reason it's not coming up and you see it through the camera, you can change your view to a side-by-side mode. And from that side-by-side mode, you'll be able to then use this section here to either make that expanded bigger and reduce the PowerPoint slide. So a couple of things there for you to be aware of. The session today is being recorded by APAN, so you'll be able to contact them for a copy. If it was APNIC, sometimes we do the recording and we'll let you know. When you join, can you make sure that you mute yourself so that way you don't disrupt the session? And if you have any questions, you can type them directly into the document, into the Zoom window here. Sometimes we have a shared document, but we don't have that today. For those people who have just joined today, just recently, I've put a link into the Zoom chat window where you can access the wiki page. That is this page here, and you'll be able to get access to the resources from there. If you have any issues and something goes wrong, maybe restart the session. APNIC's not actually supporting this, so APAN is doing that, so you'll need to contact them for support. So we've got two 90-minute sessions. The first session is going to be theory-based. I may break it up and we start doing the practical in this before the break. Then we have a 30-minute break and we come back and finish off with a practical. Now, there is a lot of theory, so I'm not going to focus too much on the theory because I want to give you some hands-on today, and we've got a virtual lab for you to go through and start working on that. What I do hope to achieve is to hopefully give you a quick overview of what software-defined networking is and a working application of that, in particular, Openflow protocol and how it can be used in a network environment. And from that, we then build up a simulated network and we connect it to different components to create our Openflow setup. So we're using our Openflow controller and we're going to connect our network simulation to that controller and we're going to influence the traffic based on different characteristics. So we'll talk about that in more detail. The resources, as I've already mentioned, are on our wiki page here. I've put a link into the Zoom chat window. Can I get everyone to do a thumbs up or click on the green tick to show that you've been able to access that page successfully? Or you can type in yes into the chat window. So thank you, Christine. Thumbs up. How's everyone else going? If you haven't got the link, I'll just put that back in again. So that way you can get that again. And this is what you will see when you open up that link. So currently at the moment, we're focusing on the agenda. We'll then access the introduction to SDN, but I've also got a whole heap of extra links on the right-hand side to drill down and go into more detail after the session, if you have that. So it's very important that you can access that wiki page. So can I just make sure everyone's been able to get access to that? If you have questions during the session, just raise your hand or type your question into the Zoom chat window or into the Hoover web interface, if you've got that. After the session, if it's a very technical question, you can send it to community trainers at apnic.net. APNIC has about 32 volunteers that are referred to as community trainers that are actually working in various industries around the Asia Pacific. And they monitor that mailing list and they will respond to any technical questions. If it's more training related to the session, you can send me an email directly. My email is in the wiki page here. You just need to replace the characters appropriate for the symbols that are there. In regards to participation, to try and make this as interactive as possible, what we are wanting you to do is I'm going to either do a quiz throughout the session or later on in the session. The more questions you ask, more interaction you have, the likely you are to win. So we have some gift vouchers that we tend to give out when we do online sessions to help encourage that participation. The main thing to be aware of though is that you can only win that voucher once every 6 months. So if you've already participated in a APNIC online tutorial and you've won a voucher in the past 6 months, you would not be eligible for that. It is also expected that if you're attending our sessions and we've got a theory component and a lab component, we expect you to do both. So completing the labs and interacting. If you haven't signed up to the APNIC Academy yet, this is the URL where you can get to that link. What we'll be doing later in the session, in the second half, is we've got this Openflow Virtual Lab. That Openflow Virtual Lab is on the Academy and you will need to have an account for that. It is free to join up and there's a whole heap of other resources on the Academy that you can access for free. Some examples of those is that there's online courses that are self-paced. We tend to run a couple of webinars a month on various topics. And we've also got the virtual labs and upcoming events that you can go and register for as well. I'll skip that. That's more to do with our APNIC policy creation and we're at APAN 54, but there is a conference coming up called APNIC 54, and that's held in Singapore in September. So if you're around that region, you're welcome to attend. If you're not able to attend in person, there is free registration online that you can access the resources, the conference talks, as well as some of the training that will be virtual. So for example, today we're looking at one section of our 5-day workshop for software-defined networking. So if you want to attend a more detailed version of this training, you can do that at the. You can do that with the attending the conference for the 4-day workshop that we've got there. So what we're going to do is start with covering some of the basics. So starting at the beginning, I'll try and give you some terminology around what is software-defined networking and how it evolved. So this first session, we'll start talking about what a router is, going back to the basics. What I might do is just, can I get a hands up or a green tick if anyone is using software-defined networking in their current infrastructure at the moment? Or have you had experience with using any of the tools that are available from the vendors, or even had a look at Openflow? Can I get you to raise your hand if you've got experience with this? Looks like no one's raised their hand. Okay. So we're going to be looking at what a router is and why you need to understand that. And then we start looking at the Clean Slate project. That then builds into this concept behind how the emergence and evolution of the software-defined networking came about. So when we look at a router, it has two key functions or two key roles. The first one is that it's going to have to figure out how to get from point A to point B, determining network paths. So it needs to learn about the network and how it can send traffic from one part of the network to another part of that network. Now, that could be just as simple as a local area network or a wide area network or even the internet. It's a matter of knowing how to get from point A to point B. So once it knows how to do that, it then needs to determine how it's going to send that packet. So it does the packet forwarding. It receives a packet, it looks up information about where that packet is destined to go to, and it figures out what is the exit path to send and forward that packet on. So that's the two simplest things that a router is doing on your network. Now, in 3 or 4 decades ago, a router was very simple. It didn't do much apart from those two functions. Now, though, today's router is a lot more complex. There's a whole heap of extra computing and other resources and services that are running on that router. So you've got different categories or different other services that you run on that. So you have a management interface, and that's going to be like your command line interface or your simple network management protocol. You also then have your services layers. So how are you going to figure out what traffic is running at what level and how you're going to forward it on. But down in the hardware, it's got all these extra processing powers now. So you've got on top of your processing, your central processing unit and your memory, you've got your ASICs, your network interfaces, and a whole heap of complexity that goes with that. Now, from that complexity, your router is still trying to do those two key functions. Learn about the network and how to get to from one part of your network to another, and then forwarding those packets. And when we look at the router, it is broken up into what's called a control plane, a data plane, and a management plane. So the control plane is going to figure out how it gets the packet sent to the next location. So it's basically the brains figuring out how it's going to get from this point A to point B. With the data plane, it's the actual process of taking that packet from this interface and putting it on this interface here and sending it back out on the wire. Whereas the management plane is a way of being able to look after that whole system and combine all that together. So we build on that to get to a very complex setup. But the thing with that, though, is as internet became more popular and networking and IT in particular is used by businesses for a lot of things now, more and more expectations were put onto our network layer. And so from that, we had this complexity rather than just simple receive a packet, send it out. Receive a packet, send it out. We ended up building these very complex devices now that run our networks. But on top of that, even though we thought about a simple way of sending communication around the world, a lot of applications were built because the need or someone saw a better way of doing it. So the internet was just a simple web page that allowed you to view information on an as-need basis. It was a static document. If you think about that way back in the early 90s, there was not much there. It was a static document, there was a link to another static document or a link to a download. Nowadays, it's used for a lot more. You've got online shopping, you've got video streaming, you've got this session that we're doing at the moment. We're doing an online meeting. So there's that unexpected use of applications. The other thing is that we don't have this flag day where all the hardware is going to be converted to the latest version, and they've got all these older equipment there, so it has to have that backwards compatibility. The other thing is, if we look at this model on our today's router, is that everything is stuck on that one device and everything is running on that one device. And that can add for basically this tight coupling between the different planes. So the data plane and the control plane and the management plane. And so that means the performance is getting better as well. Approximately 12, 13 years ago, they decided to get a whole heap of researchers and vendors together and pose a question to them about what's called, if you were able to redesign the internet, how would you do it? And how would it look like in 15 years? So this is quite an interesting sort of topic. If you were given that yourself, everybody would come up with a different design. And that's what the Clean Slate project was. So late 2009, they got a group of researchers together and they posed this question to them. So if we know what the information that we have today, how would you redesign the internet or that global communications infrastructure? What would you do different, or what would you improve, and how would you do it? And then thinking about that, how would it look in 15 years' time? And we'd get a completely different answer today compared to 2009. And so that was the idea behind that. So we had this Clean Slate project, and they basically came up with this research called Openflow and Software-Defined Networking. And they wrote this paper called Openflow Enabling Innovation in Campus Networks. If we go to the wiki page, you will see here, I've got a link to that document. Let's copy that link address and I'll put that into the chat window for you. So you should get access to that. And so that's a quick overview of what they were trying to achieve and how they were going to do that. Essentially, what they were saying is that we've got this tight coupling. So we've got our data plane, we've got our forwarding plane, and they're on the one device. If we were able to do a Clean Slate project, how could we do that? And in this case, it was looking at the campus network, but we could extract that out to other types of networks as well. But the main problem was that you had your hardware and the software was on that hardware. And you had various vendors that had different mechanisms used for that software. So it made it a little bit difficult. And essentially, we had those two roles to do, which was figure out where to send information on the network and then do that packet forwarding. And so what we were trying to do is to remove this tight coupling. So the software and the hardware should be able to be separated out into a different location. So that's what they came up with. They said, okay, why don't we take the control plane which has all the different protocols and the mechanisms that we use to calculate the forwarding paths or the best path. And we've also got the data plane, which is how we send the packets out on the network. So we've got those on the one device. So we've got things like our routing information bases all on that one device. Could we potentially take that and separate those out? And we separate those. So we still have our hardware that does all the data plane component that is sending the packets onto the wire. And let's separate the control plane and put it into what's called an Openflow controller. So remember, this is 13 years ago, 2009. So that control plane used a secure channel to communicate from the hardware, your router, to that software or the Openflow controller, called a secure channel using a protocol called Openflow. And so the idea behind that is now that we've got this way of influencing the decisions on our hardware. So you could potentially have one or more hardware devices communicating to the one Openflow controller. So it gets a better view of what's happening. The other thing then is that when it has that better view, the telemetry of your network and how the links are going, it's able to make better calculations or decisions. So we can go from this concept where we've got our Openflow controller. It does all the calculations that we need for our network. And then based on that, it's either going to add or delete or modify our flow table entries. So when a packet comes in to the hardware device, it needs to make a decision on what is the best way to send that packet onto the network. So that information gets sent up to our controller. The controller has an overview of the topology and it makes a decision on that. So if it hasn't got any flow entries into this hardware device, it will add it. And then after a period of time, it may remove that. So if you think about our devices as a simple, dumb hardware level, everything that it needs to do, it communicates to the controller first. So the controller is going to use what's referred to as these header fields. And based on those header fields, it's going to match something. It might be as simple as our source IP address, our destination IP address or destination MAC address. It then determines if there's a match, what action needs to be done with that packet. And it then sends a message back to the hardware device as a flow entry. So it'll have flow 1, and whatever the match was, it will say forward to port 11. Flow 2, drop it. Everything else, depending on what's happening, it might be just as simple as send it to the controller, and then the controller makes a decision on that. Some of the header fields, if you think about the most common header fields that you use in your network, it's going to be things like, which port did you get this traffic on? What's the source and destination address? Is there a VLAN ID? Remembering that this is looking at the switch. What is the IP source and destination address, the protocol that's used, the service, the layer 4 port, destination, layer 2 port. Now, depending on which version of Openflow, which I'll discuss later on, there's going to be other fields that they can match on as well. Once it's got that match, it will forward that based on the flow that it needs. And the advantages of this is that you'll have one controller that could handle multiple switches at the same time. So based on that, we're going to use our Openflow capabilities. Now, this is back in 2009. So a lot of people saw Openflow. If you implemented that, you had a software-defined network. That is one of many components today of the software-defined networking architecture. There are a lot of other protocols out there and updated protocols that are there. But the main concept behind it was that shift of having everything decentralized on all the hardware devices to come to this centralized controller. So when we look at that centralized controller, what we're doing is we're decoupling the physical component and the software. And we're putting the software in a remote location to make those decisions and then tell the hardware what to do with that. And so you have this consolidation of your networking. And you can centralize that, and you can have, instead of a one-to-one correspondence, you can have a one-to-many correspondence with one controller and many switches and devices. So from this point of view, though, if you only have one controller, what about scalability? If you've got a very large network with thousands of hardware devices, how are your controllers going to handle all that traffic? So there's an issue from that point of view. And when it was first designed, you could only have one controller on your network. So that made it one controller that your devices could communicate with. So therefore, you had a single point of failure because you didn't have redundancy in place. And then as they progressed and changed the Openflow protocol to allow more than one controller per hardware device, what about the consistency? So how do you keep your controllers in sync with what's happening on the network? And so there was some challenges with that. So when we think about the birth of software-defined networking, it's the process of separating the control plane and the data plane. Now, that wasn't what it was meant to do, but it was a consequence of that design, that open Slate project. What it did do, though, is it brought in a new era of programmability. So being able to dynamically program your network based on certain criteria, rather than you having to manually set up your network and have it as a static system that you dynamically had, or not dynamically, but you had to go in and manually change. You can now receive packets. The controller can look up an action, look up a match, and then do an action based on that. And so it allows for that programmability. And we've got things like RESTconf, NetConf, and a few other things there. And one of the first articles to coin the term software-defined networking is available on that link there. You're welcome to go and have a look at that. So from a software-defined networking point of view, Openflow was a starting point. And we're going to look at that today in the lab. We'll be able to add a flow entry using some programming or a command line interface. And so that way we can tell it to do an action via a program if we would like. By decoupling that control plane, it means that we're going to have a capability of having some sort of way of building up our resiliency and scalability. Because if we can have multiple controllers and they can stay in sync, it means that if your devices have multiple paths to those controllers, something goes wrong, you can still get access to those. When we look at our Sdn architecture today, most routers today will hopefully support a hybrid approach. That means that they will allow your hardware device to have a control plane on there, but also to communicate to a centralized Openflow controller of some sort. If it's an older equipment, then it may not be able to do that. But the idea is that when we look at our Sdn architecture, we have this hybrid model of Sdn. So we have our data plane, And then from our data plane, we're going to put a proportion of our control plane into some sort of centralized area. And depending on that proportion is how far you are in the SDN. So if we have a look at this was written a few years ago, but a lot of smaller networks usually have all of their control plane and data plane on a decentralized location, so on each device. If you go to a fully automated network, you would have the Openflow model where you have your data plane on the device, but most of it, your control plane, 100% of it is in a centralized location. It's completely decoupled. Whereas what we're trying to achieve today is just a hybrid version of that. So you can still leave it to do that. So when we are looking at defining our software-defined networking, we need to think about it from this point of view. There is no one definition for software-defined networking. Different vendors, different organizations have their own interpretation of what a software-defined networking is. So depending on who you're talking to, it's going to be all sorts of things. In regards to the Open Networking Foundation, they're one of the big drivers for the software-defined networking and some of the projects that are working towards that. They've defined it as a physical separation of our network control plane from that forwarding plane, and where the control plane controls several devices at once. But from our point of view, we're just basically going to say that SDN is a new approach to networking that provides a greater network agility and flexibility by these three steps. Basically, automation using some sort of programmability, disaggregation, and abstracting that layers, and hopefully having that centralized control plane with full visibility or a real-time network visibility of your network. So essentially what we're trying to achieve is this agility. So being able to bring up our different networks or overlay networks in a faster time frame, and with less human interaction. That way you get more revenue. From an automation point of view, that's where the agility comes in. And then if you're looking at the costing of the different devices, so reduction in your hardware network operation costs, you can get savings for your CapEx, your capital expenditure, and your operational expenditure. And then hopefully you can have end-to-end optimization. So if you've got complete real-time network visibility, and you can see that you've got links that are congested, you may be able to dynamically reroute your traffic to hopefully mitigate against that. That way you've got that end-to-end service and network management in place. Some of the organizations that are involved with the software-defined networking, IETF, ITU, ONF, the Open Networking Foundation, the Metro Ethernet Forum, and the Broadband Forum. So can I get you to go to the wiki page? And in the wiki page, we have a whole heap of resources here and a catalog of tools. Now, sometimes the links are working and sometimes they don't. So I'll put in an alternative link there. Today it is working, so that's good. So what we've got here are a link to the different projects and resources that are available for our software-defined networking. So on the left-hand side are the organizations involved with creating the standards. On the right-hand side are the open source projects, the software to run those different standards that people are writing about. So from here, you can see that the Open Networking Foundation is the conduit between those two types of organizations. What we do have in this page then is a link to all the different resources and projects for you to get more details about each of those. Today, we're going to be looking at the Open Daylight project and set that up in a lab environment. But you can go and read more about these network infrastructures and the standards defining organizations for that, if you would like. Are there any questions so far? Doesn't look like there's any questions. So to give you a visual idea of the Sdn architecture, so this is from ITU. What we have is we've got our network resources in the bottom layer, so down here. Our network resources. Those network resources are going to talk to our controllers, and then the controllers are going to be the middleman between your applications. And so we'll break this down into a little bit more detail, but this is essentially what we're looking at from an IETF point of view. So we have our devices and resource abstraction layer, our DEL. So it's got our networking devices. They're going to talk to our control plane and management plane using a southbound interface. And then from our control plane, we're going to be talking to our applications using some sort of services interface. So RFC 7426 talks about that in more technical detail, but essentially you're going to have some sort of communication, and your control plane is going to be the middleman between the application and your hardware devices. This is the framework that we tend to work with, and it breaks it down into all the different types of services and activities that you try to do in a standard network. So you've got your data plane, so your hardware devices, and on those hardware devices, you're going to have different functions or services that you need to do. So for example, communication to other networks and other devices, border gateway protocol. You've got your routing information bases. You've got your, in this case here, one of the newer features of Sdn is the Path Computational Client, or PCC, which allows you to influence how you do your traffic engineering. And that's where we can build onto our segment routing and our resource reservation traffic engineering concepts there. But the idea is that we are going to be looking at today our Openflow protocol and being able to talk to our controller using this Openflow protocol. In our 5-day workshop, we break it down into a little bit more and look at some of the other services, but that's what we'll be looking at there. Now, it still uses a southbound interface to talk to our controllers to have that communication, and we use a northbound interface to communicate to our application. In the lab environment, we're going to use the Cisco Openflow Manager to be able to emulate an application, and we're going to use our Open Daylight controller for our control plane. If we were having to have multiple controllers, you're going to have some mechanism there that goes east and west. So this is important to understand. I find that this is a nice little visual representation of that. So when we're talking about our application plane, it uses our northbound interfaces to be able to talk to the controller. So the application plane is going to consume your network. It's then going to allow you to push down configurations to the controller, and the controller can make those changes on the hardware devices. So it's abstracting that information using various mechanisms. So it's either going to be using an API, application programming interface, using netcom, RESTcom, or a YANG model of some sort. And we'll see an example of that in the lab today. From a control plane point of view, that's going to be the planes of the operation. So it's going to learn about your topology. It's going to then make decisions based on that topology, how to do the resource management and the traffic engineering if you've got that programmed in there. But hopefully it will help with regards to which route to select and to tell the devices how to send that onto the network. And then you've got your data plane. The data plane is the hardware devices themselves. And so they're going to basically figure out what we're going to do. It receives a packet. It then communicates to the appropriate service in the controller, and the controller makes a decision, sends it back to the hardware device, and away it goes from there. From a use case point of view, there's various types of use cases that you can have. One of the more common ones is in our data center. So if you think about Azure, AWS, Google Cloud, or even your own data center, if it's a very large one, you're going to have this underlay network that is the hardware, and you're going to have various tenants that are going to subscribe to services. Those tenants are going to need some sort of network connectivity. So you can use the software-defined networking to be able to basically have a multi-tenant environment that creates an overlay network to allow that communication between their devices. And so that allows that automation side of that, rather than having to get your engineers to manually go in and create that. That then builds up to this service automation provisioning. So think about Azure, AWS, Google Cloud. I sign up to the service, I go to a portal, and I start creating my virtual machines, my virtual networks, and it dynamically creates that in the background, and it builds that up for me. I'm able to modify different things on that web portal, and that's where we have that capability. What about network optimization? So if I've got real-time network state information about my underlay network, I can then determine how to run my traffic so I optimize my throughput. So I can run it what's referred to as a hotter network, running the network's hotter because I'm basically sending traffic through everywhere. There are lots of open source projects out there. We're focusing on the Open Data one today, but there's also the Open Network Operating System, the owners. Unfortunately, we don't have a lab yet. I haven't had time to write one. We'll watch this space. Hopefully we'll get something there. So the main thing is that we've got this software-defined networking architecture. One protocol is not that. The software-defined networking utilizes multiple protocols. So it's not Openflow protocol as such, it's a combination of different frameworks and so on. But it allows you to enable the principle of centralizing your control plane, having some sort of abstraction of your networks and topologies, and being able to program those for you. So from enabling our software-defined networking, we're going to go from our traditional network that's static or you change dynamically. You can do something, one or more of these. So if you've implemented segment routing and you're using path computational element, then you have Sdn. If you have Openflow set up for your switches, you've got Sdn. If you've implemented some sort of API programmable networking using netconf or Yang. You've got Sdn. It's basically a combination of all of these different services that allow you to build up a Sdn network. The network function virtualization, comparing that to our software-defined networking. So software-defined networking removes the elements of the control plane from the data plane, whereas the network function virtualization basically takes network software from the closed proprietary hardware systems and makes it a little bit more open. So that's the idea behind it. So we basically take it from this hardware vendor-driven software and hardware to this generic off-the-shelf hardware, and then you have your virtualized software that runs on top of that hardware, that generic hardware, rather than just being vendor-driven. So that you've got more and more virtualized devices. I'll just drop out of that because you don't want to know about the 4-day, 5-day workshop, so we don't need to worry about that. Any questions about that so far? Doesn't look like we've got any questions. So we're going to start focusing specifically on the Openflow protocol, and we're going to go into a little bit more detail about that. And then we'll start building our virtual lab environment. What I might do is that I'll start with going through it very quickly, some of the terminology. Then we might break and go to start the virtual lab and then come back, because I just find it a little bit easier if you've done some of the installation and playing with the Openflow controller. It makes it easier to understand the theory. So what we have is the Openflow protocol. As I said, version 1 came about because of that OpenSlate project in 2009. It was handed over to the Open Networking Foundation in March 2011. And there's various iterations of the Openflow protocol. So version 1 was a very basic version. And as they implemented it, they said, oh, maybe we should do this. And they fine-tuned it and they had various changes to that. So 2015, version 1.5.2 was released. So from a history lesson point of view, we can see here version 1. Some people see it as being December 31st, I think, as being the 2009 when it was first implemented. Some people see it as being 1st of January 2010, but it's actually 2009. We'll focus on version 1 to start off with, because that gives you the underlying theory, and then we'll move to version 1.3 and just cover that in detail, because that's the most common implementation of the Openflow protocol. When we look at the Openflow revisions, what it created in summary, the first one, version 1, it had this 12 fields that you could match on. So remember, we looked at that screenshot, we looked at that couple of slides ago, where we had that flow entry coming in, flow 1, flow 2, flow n, and the fields that were matching are referred to as hard-coded 12-tuple match. It had a single table, meaning that it could only have one flow entry table where it's stored and looked up. In regards to version 1.1, it allowed you to have multiple flow tables, but it also allowed you to group those tables and have instructions and other metadata. It supported some other protocols, including MPLS. Version 1.2, I might just bring them all up, so it makes it a bit easier. Added support for IPv6, as well as having multiple controllers. Version 1.3 started to add what's called a per flow meter and a table miss flow entry. So that way, if it goes through all your flow entry tables and it still misses, you can have a default action if you want. 1.4 added some more extensibility to the protocol and added some extra features there. 1.5 added egress tables and some other extensions and statistics. So essentially what we have is our Openflow controller. We have our hardware device, and on that hardware device, we have our flow table, and that hardware device is referred to as an Openflow switch. So the flow table is basically a single entry. It allows you, sorry, not a single entry, it's a table that stores the flow entry. And it specifies what to do with that match condition and the action that is resulted from that. It also needs to support some sort of secure channel to communicate to the controller. So you need that connectivity with that. So we have the flow table, which will have the packet match criteria, that is the header field. It's going to have one or more actions that are associated with that header field that you're matching on, and any counters related to that. So we've got these match fields that we've got. So we've got things like our ingress port through to our MAC address details, the ether type, the VLAN details, our IP addressing details, and what ports you're going to be using for that. The actions that we can choose to do with those matched fields are one of four categories. So you've got forwarding, and that's going to be mandatory. So what are you going to do with that? Or it's going to be a drop. So if you haven't got a forwarding happening, it's going to be a drop by default. Then you can do an optional, send it to a different queue if you wanted to do something else with that packet rather than just that one action. Or you can do a modified field. So being able to change that. An example of that might be that if you've received something from this source address, change it to this source address. Or if you've got anything destined to this address, change it so it goes through some sort of network listener of some sort. So the supported actions that you've got, as some examples here. Output it to a specific port on the switch. So remember, you've got an ingress port and you've got an egress port. You can modify your VLAN IDs, your priorities, or you could take out that VLAN altogether. You can modify the different source and destination MAC addresses. You can modify the IP addresses for the source and destination, and the type of service. You can modify what that's going to be or set it if you're going to. And you can specify what queue to send it to if you want to add some extra details there. So that's at the very basics of those. So you basically get your packet come in, it gets sent to the controller. The controller is going to look at the fields that it can match on. If it can match, it's then going to do one of these actions. Any questions? So we're going to focus on 1.3 and drill down into a lot of detail. From an Openflow point of view, it's the fourth major release, but in the packet capture, when you look at it, it's going to have this wire protocol of 0.4. There's various updates to that, so version 1.1 through to 1.3.5, and it basically changed it and was released March 26, 2015. What I'll get you to do is go back to the wiki page, and I'm going to give you a link to a Openflow packet capture. I just find it a little bit easier to describe things when you can see that. Can I get everyone to open up that packet capture? What it does is that if you've used Wireshark in the past, you can download the file if you would like, or this is CloudShark, which is a web-based version of Wireshark. It has limited settings compared to other ones, but that link I've given you there, I've already put a filter in there for you. I've said to basically just show me the Openflow version 1 protocol for this packet capture that's happening here. So I'm just going to zoom in over here so that we can see that. So I'm just drilling down on the packet. So I'm looking at the very first packet here, and you can see that it's Openflow protocol, and it's a Openflow protocol, which is the hello. We've got a hello, a request, a reply, a request, a reply, and so on. So we've got different types of information that's happening. So essentially, if you think about your TCP protocol, you've got a three-way handshake to start your communication. That's the same with the Openflow controller and the Openflow protocol. We're going to need to have the communication start. So the controller is going to open up that secure channel, and it needs to know about your Openflow switches capability. So that's why it's doing that feature request, and then we're getting replies based on it. So if we look at this Openflow 1.0, and if I have a look here, this is the field I was referring to in regards to the version 1.0. On the wire, it's saying that the version is 1x01. If you're looking at 1.3, this would have 0x04. So there's not much to say there, but that's our Openflow protocol hello command. So that's why I'm getting you to have a look at that. We'll come back to that packet caption. Just keep that open at this point. In the 1.3 version, it allows us to have this framework. So we have statistics, but that got renamed to the multi-part framework. It has this table missed flow entry. It's got per flow meters, and it's got the other resources there that I'll drill down on. From an Openflow point of view, there are two types of switches. There's what's called an Openflow only switch and an Openflow hybrid switch. The difference between them essentially means that if it's an Openflow only, it can't send packets without being able to communicate to the controller first. So that means it's not going to be able to get any flow entries if it can't communicate. Whereas if it's an Openflow hybrid device, it can still work as a standalone device and forward packets without communicating to a controller. So most networks should have something that is an Openflow hybrid these days. So we have our Openflow environment that is set up to this. So we have our controller. It communicates over a secure channel to our hardware device using the Openflow protocol. Inside our Openflow logical switch, we have this Openflow channel that's sending packets back and forth. We've got our packets that come in, and it's going to create these flow tables. Now, there may also be a group table, and we won't go into it in much detail today, but it allows us to group some of our actions. So the Openflow controller is the interaction between the Openflow switch and the Openflow switch protocol. Our group table allows us to have our data paths that allows us to switch traffic directly and speed through the network. So our flow tables are usually made up of what's called a match field, a priority, a counter, instruction, timeout, and some other settings there. But essentially, we're going to decide on our header fields what are the match. If we have a priority, it's going to allow, think about your access control list. If you receive something in, it looks at that priority and makes a decision on that and how it adds that through the processing of our pipeline. We'll look at that when we look at the lab to build on that. I might actually stop there and get everyone to log into the lab environment just to make sure that we got access to it, and we'll start building it out. So this will make sense once we've done the hands-on component. So can I get everyone to go to the wiki page? Just pasting the virtual lab into your Zoom chat window, so you should be able to get access to that. Can I get everyone to click on the link and do a thumbs up or use the green tick to show that you've been able to access the Academy page? So we've got this Openflow Lab that you're going to get access to here. So you'll need to log in to the Academy. I'm just going to click on login. If you haven't got an account on the APNIC Academy, when you click on the login, you can click on the register here. I'm just going to take this off screen so you don't see my login details. Once you are logged in, you'll be able to see that you've got this launch lab component. One thing to point out, I'm not too sure where you're located. So the data center location, you can change where you're going to start your virtual lab to get better performance. If you have high latency, it can cause some weird interactions with the virtual lab. For example, if you have a latency greater than 250 milliseconds, it will put in extra keystrokes when you're typing, and I find that very annoying. So if you click on the data center location, you'll get this extra field appear, and you can then change it to one of 4 data centers if you would like. Or the Academy will, in my point of view, if you just leave it turned off, it will take you to what it thinks is the closest data center to you. So it comes back to whether you're running a VPN or the way that your network is connected to the internet. So I've got Christine doing a thumbs up. Excellent. Who else has got access? So once you've got access to the virtual lab, please let me know. I'm just going to click on the launch lab. So this may take a couple of minutes to launch. So what we'll end up with a environment where we've got two Linux machines. One's going to be our network simulation machine using a software called Mininet, and the other one will be our centralized system that we use to configure our Open Daylight controller, the Openflow, the Cisco Openflow Manager, and we can also use it to communicate with our Mininet system. So you can go and get more details about our Openflow controller, but this is what we've got as our lab environment here. So you can see here, we've got our two Linux systems connected via a switch to each other, and the base IP addressing for IPv4 is 192.168.1. Our Mininet network simulation is on .100, and our Open Daylight controller, which is that graphical user interface that we're going to log into using Ubuntu, is 101. To give you an overview of the interface for the virtual lab, on the right-hand side are the instructions and the different tabs that you've got. So you've got instructions. If I click on resources, it shows those two devices that we've got access to. And it also shows you the username and password for that. So if I click on this symbol that looks like a T, that allows me to type text into the virtual lab window, and it's going to type that password in there for me. And I can just click into that left-hand side to get into that virtual machine. I click on the instructions, and that takes me back to that location. In the top right-hand side, I might just do some annotation on here so you can see it a little bit better. So this is the resources tab where you can see the password and change between the virtual machines. The current virtual machine that you're on, the name of that machine is in the title here. You've also got this lightning icon, and that's where you can access your environment's variables to send keystrokes, type password, type username, as well as to paste in settings from the clipboard. If you have network problems, you'll see that here. And if you do have network problems, this monitor icon here allows you to try and refresh or reconnect to the network, as well as if your screen doesn't go full like this, you're able to then change that around if you would like from that point of view. Up in the top right-hand corner, I refer to this as my hamburger icon. You've got access to things like saving your lab. So when we have a 30-minute break, you can save your lab. So that way it doesn't time out on you before the end of the day. And if you're halfway through something and you get called away for work reasons, you can save the lab and you can come back tomorrow if you like to continue the lab, if you like. So I'm just going to get rid of my annotation, and you can see here when I click on the lightning bolt, I've got this type text and I've got this type clipboard options there, as well as some other keys that I can use. And then from the monitor point of view, I've got things like resize bit machine to window, reconnect if there's a network issue. So I've got a question about, can I do the lab later because I'm on a mobile? Yes, you can do the lab later. This is open 24/7. You can do it anytime. As long as you've got a login, you can go in and create that. So if I click on the next option here, it's going to take me to the first set of instructions. So the first part is to get you familiar with the network simulation software. Now, to get access to the Mininet simulation software, that's running on a separate Linux system. So I click on that. Now, one of the limitations with our virtual machine environment, when it's just a command line interface, notice there is no scroll bar here. So that's a bit of a problem because some of the outputs are going to be quite different depending on what you're trying to achieve. So the login for Mininet is Mininet and the password is Mininet. So notice there is no scroll bar in this section here. So I'm going to have an issue if I want to get access to that. So what I'm not too sure if that it doesn't support that. Hold on. So what you can do is that I'm just doing an ifconfig and I'm looking at my IP address here, which is 192.168.1.100. And I can pull that out a little bit easier. So that's the address that I'm grabbing. So I just want to grab that address and I can go back to my GUI interface and use a terminal window from there to access this system via SSH. So let's go back here. And it's not APNIC. And this is going to connect to the system. Now, for whatever reason, there's a bit of an issue. We were trying to communicate and start up, but eventually you will get a prompt for the password. And now I should see I've got this scroll bar on the left-hand side, even though I'm not scrolling at this point. So that is the first part, is to get connected to your Mininet controller. Oh, it doesn't support the brief. No. So now that I've got access to that, I'm going to create a very simple network. And as you can see, I'm going through these different sections and I just put a green tick next to what I've completed. So see, I've got the green ticks coming down. That way you can keep track of what you're doing as you go. So the first part is that we're going to create a very simple network. So we're saying, go ahead and create a Mininet network and make the simplified MAC address for our network. What that means is that instead of having a random media access control address created, you're going to have an address that's all zeros. And then if it's host 1, it will have 1. If it's host 2, it will have 2, host 3, and so on. So it just makes it easier to know which machine you're communicating with. So I do a sudo mn --mac and then -- controller equals, and I'm just going to specify none. And this is now created. Notice how I've now got the scroll bar, so I can scroll back up and down if I want to. Now, what I should do is make that a little bit bigger so it's easy for people to see. Edit my preferences, custom font. And that makes it easier for you to see. Can everyone see that a little bit better? Thumbs up if you can see it. Resize my screen. That's not been resizing. That's it. So what this has done is it's created a network with these nodes. So if I type in the keyword nodes, it's going to tell me I've now created this 3 machines, host 1, host 2, and a switch. Just start with my annotation so that way you can see what I'm referring to. So here's the command. I said Mac controller equals none. So what it's done is it's created a network. It's, even though it's saying it's adding controller, you can see that there isn't one. Then it goes adding host, and it's added host 1 and host 2. Adding switch, and it's added switch 1. And then it's created the link between host 1 and switch 1. And then it's created a link between host 2 and switch 1. And notice there's nothing here for our controller, even though it's going through that process. So when I type in the keyword nodes, it will show me the 3 systems I have set up for that network. Some other keywords, if I want, I should be able to get rid of my annotation. I do a question mark, it's going to tell me all of the different one-line commands I can do. So I've got things like nodes, link or links, dpctl, which we'll use during the lab, dump, net, ping, source, and so on. So we can go through and have a look at these different components to see what's happening. So let's have a look at our network command. We can see here how the devices are communicating with each other. So we can see that host 1 is connecting via Ethernet . So we've got host 1 connecting via Ethernet 0 to switch 1, Ethernet 1. So this is like saying that we've got this device here. We've got host 1, and it's specifying the physical port there and the port there for our switch. So this is S1. The same for our host 2. It's got Ethernet 0. Ethernet 0. Not. I'm drawing it that way, let me. So based on that, we can see how they're physically connected, even though we're playing with a network simulator. So that comes in handy for when we want to do our matching on fields. We can figure out what the ingress port is and then decide an action to do on that. If we had a controller, we could dump the flow entries to see what's happening. And in this case here, it's just showing us the processor IDs. It also shows us the IP addresses for our devices. So it makes it a little bit easier for you to determine what's happening. And if we use the dpctl and we look at our flow entries, Close. We don't have anything there because we don't have any controller set up at this point. So if we try to do a ping, host 1, ping, host 2, we won't get a response because we don't have any we don't have any flow entries at this point, so it's got 100% packet loss. So it's a very simple network. And without being able to communicate to our environment, our Openflow controller, it's not able to do anything. So what we can do is exit out of that and set it up in a very simple network by saying dynamically create a controller for us. And we can see here now it's added a controller, C0. If we do the same sort of process, if we do a dump, we can see that we've got our 3 devices similar to what we had previously, but instead of being just a switch, it's now got an OVS, Open Virtual Switch. It's also got a controller, and it's saying the port number 6653 to communicate on if we want to get access to that. So if we do a H1 ping H2, we now get a response. So we have that connectivity because the controller is able to do a match on a field and send a flow entry. And that match at the moment is it's going to say, allow the packet to get there. Same sort of process as before. We can drill down on the nodes, the network, and see how things are connected. Notice there is no communication to the controller. So how is it got that secure protocol? This is an out-of-band communication. So it physically needs to be connected to the controller, and there still needs to be some sort of connectivity, but it doesn't get shown in the simulator. Okay, so just be aware of that. You still need to have that physical connection, but it's seen as a secure channel, so it's not going to show you the details there. If we do a DPT CTL dump flows, notice there's nothing in our flow entry at this point. But if I do a H1 ping H2 for a count of 2, we are getting communication. If I arrow up again and do the flow entries, you will now see that it has some flow entries there. And what will happen is that there will be an expiration for those in the table. And if there's no packets sent within that expiration time frame, then it will remove those flow entries. The reason behind that is how many packets flow through your network. And if your switch had to remember every flow entry for every packet it receives, it's going to need a lot of memory. So let's break this down. So things that you will see is that this is using a table equals 0. It's got an idle timeout, which is what I've mentioned already, that if it hasn't received something within that time, it's going to be aged out. It's got a priority of 65535. It's specifying protocol as being ARP, import equals 1. There is no VLAN details. It's got the MAC address as being 01. Destination MAC address is 02. So it's coming from host 1 to host 2. We've got our IP address for our source, our IP address for our destination, and the action, in this case, the controller is saying send it out to. And if we have a look at our annotation. Oh, I can't, I'm in edit mode. Sorry, in annotation mode, so I won't let me type. We can now also see if we're going to get a response. So that's destination. So here we have the MAC address as being 2, destination is 1. So that's the response from that ping packet. IP address from router 2 to router 1. The action is output 1. And you'll see that building up on that. We can also see that we've got our ICMP, actually, there it is here, ICMP 8, ICMP code 0, what to do with those. So if I break that down, and I've been talking for a little while now, so that should have given enough time out for our flow to be deleted again. Can everyone see that? Any questions? What I might do is I'm just going to exit out of this one at this point, but we'll save our lab at that point, because up here you can see that we've got 2 hours and 39 minutes, which is plenty of time because we finish in a couple of hours anyway. But if you want to pause your lab and have a coffee break or morning tea break, click on the hamburger icon here and click on the save, and you'll be able to save that and come back after the break. So I'm just going to do that. And you'll see that when I save it, I've got this continue in this environment here. So we're going to have a 30-minute break. So stretch your legs, get a coffee, have morning tea,